I wanted to just begin by showing you how you can directly compute the character variety for the figure 8. I've only done the computation for irreducible representations. As we talked about, the reducible representations form an entirely separate component, and it's not hard to see that this is given by r equals 2. Okay, we talked about how the trace of the commutator elements are 2, and that can give you that in the abstract, or you could compute it out in a similar way to how I'm going to demonstrate. So I've outlined 2 different methods you could use to do it completely hands-on. So for the figure 8, taking this 2-bridge presentation of the knot, then I'm just going to look at the irreducible representations. It's an easy exercise in linear algebra to show that if you have 2 generators, you want to make an irreducible representation. Up to conjugation, you can take one generator to be upper triangular and the other to be lower triangular. And we know conjugation doesn't change the trace, so I have no control really over the A and the A inverse, but I can conjugate so that this is 1. So again, you can just, if you're bored, do the little linear algebra exercise. And then you can have a free variable here in the 2-1 entry of where the second generator goes. And just to simplify notation, I've decided to write mine as 2 minus r instead of just a standard, x or something like that. So I talked about the fact that the functions defining the character variety are the values of the chi row. Remember, chi row goes from what am I doing? Gamma to C, and giving gamma, chi row of gamma is just the trace of row of gamma. Okay, that's what the chi rows are. So we talked about the fact that the character variety is defined in terms of the variables chi row gamma for every gamma in your group. Now another easy exercise will convince you that if your group has n generators, there are standard trace relations, which maybe Ilya mentioned, I'm not sure, someone mentioned them, that say that you can write the trace of any multiple of 4 generators or more in terms of linear combinations of traces of fewer generators. Okay, so for example, you can write chi row of gamma 1, gamma 2, gamma 3, gamma 4 as a polynomial in the other ones. So that means that I only need to consider, I could just, instead of any time I wanted 4 elements, I could just write it in terms of the other elements. And in terms of algebraic geometry, the structure of the set will be exactly the same. So I can officially define an isomorphism, projecting off this variable. Okay, so you only need triples, and in the case when I have 2 generators, all I actually need is the chi row of one generator, chi row of the second generator, and chi row of their product. Okay, again, this is just a linear algebra exercise in 2x2 matrices. Okay, so if you look at this relation, this means that alpha and beta are conjugate. So chi row of alpha, that's a trace, and chi row of beta have to be the same. So that's why I've put A and A inverse on the diagonal of the beta entry. Again, a little linear algebra tells me I can write it this way and not the other way for this particular group. So that means I have these 2 matrices, since they're conjugate, chi row of alpha and chi row of beta are the same. Let's call it x. That's our one variable. And chi row of alpha beta inverse, that's the other one we need. I'm going to call it r. And that's why I chose to write it this way. If you multiply out this by this inverse, the trace will exactly equal r. Okay? That's why I put 2 minus r instead of using a variable x. Okay, so this R, if you do the calculation, exactly is corresponding here. Okay, so I have variables x and r. So what do I do to check that it's a representation? I need the defining word to be satisfied. So I need rho of this w, rho of alpha to equal rho of beta, rho of w. So if you do the computation written like this, if you multiply it out, you get a matrix that looks exactly like the one I've written, where you get these identically equal to 0, and the off diagonals being the same expression, but the 2, 1 is multiplied by an r minus 2. That means to be a representation, you need star to equal 0. Right? So rho is a rep if and only if star equals 0. Okay, but the character variety needs to be written in terms of the traces. So what I have to do is write this in terms of the traces. So R is already my trace of alpha beta inverse, and I need to eliminate the A's in order to introduce X's or R's. But A plus A inverse is X. So x squared is a squared plus a minus 2 plus 2. So this is x squared minus 2. So my equation is r squared minus r times, what do I? Oh, I didn't include the 1. I thought, no, I can't do basic arithmetic. So my defining equation looks like this. So x gamma 8 sits in a subset of C2, and the ideal is given by the vanishing set of f. F of xr is that equation. Okay, so if you fiddle with this equation, this is actually birational to an elliptic curve. Did I write it down? So this is birational to the curve that's given by that polynomial. So just to give you a little picture, this is the way it sits. It has 2 points at infinity, and it intersects the reducibles. I'm going to make my r equals 2 look a little less flat. Intersects the reducibles kind of like this. And remember, there are 4 discrete faithful representations. There are 4 because of orientation reversing and lifting of the signs. And then there are an infinite number of Dane's surgery points on here. Because by Thurston, we know the dimension of the canonical component is 1. And all of the Dane's surgery points correspond to complete hyperbolic manifolds, all but a finite number. And by Thurston, the dimension of their canonical component is 1, so that manifests as points. Okay, so that's kind of what it looks like. And I just wrote this. There's another way to do it. You can show that the functions are generated by looking at words of this type. If you write your full relation as y, so that word w alpha w inverse beta, so my presentation would just be that y equals 0 as a relation, then if you say that, well, the trace of the relation has to be the trace of the identity, because the relation has to go the identity, and then just multiply by the generators, then you get the same equations. So in practice, this is often the better way to go. Okay, so now I want to talk about the A-polynomial. Let's see. All right, so the A-polynomial is basically the image of the character variety under the map that just looks at what is going on with meridian and longitude. So to do this formally, then here I'm just going to talk about a not complement, because otherwise, we need a meridian and longitude, and to do it in this dimension, we need one of each, 2 cusps. I have too many meridians. There are generalizations to link complements and stuff. But what I'm going to say, it only really needs to have one cusp. It doesn't have to actually be a not complement in S3, but nicer properties are true for these. So let's just talk about these. So I have a meridian mu, and my longitude L. Okay, you can really pick any generators for the homology and use them, but we'll just think about the standard meridian and longitude. Then the way to construct the A-polynomial is to start from the representation variety. And I just want to consider representations where my meridian and longitude go to upper triangular matrices. So RU consists of representations sending mu and lambda to upper triangular matrices. Okay, so it might look like this. And that. And the basic idea is we just want to, in an appropriate way, instead of recording the full data about these representations, just figure out what's happening with the L and the M. Okay, so what I'm going to do is define an eigenvalue map. L comes before M. And for a representation, I'm just going to read off the eigenvalues. Okay, so let me say this right. So this is going to go from R, U to C. And I'm going to take a representation rho, and it's going to spit out what the longitude and meridian are. So the image of the sort of modified representation variety is an algebraic, is in C2, right? Meridian and longitude, I have 2 parameters. And then it's an algebraic variety. I mean, maybe technically it's like a pseudo variety. I might have some holes in it, but I'll just say it's an algebraic set. But we have to be a little careful. So essentially, morally speaking, this image is the A-polynomial. But we might have to throw away a few things. So like we talked about yesterday, the character variety could have lots of components. Right? I mentioned that for any n, there's a knot such that the character variety has more than n components, different irreducible components. Some of those components might have a high degree. So we have to be careful on a component by component basis what the images look like under this map. So what we do is we take, for every irreducible component, let's say R1, in RU. And I'm saying character variety, but the character variety looks almost exactly like this because I've conjugated it, right? And the character variety for irreducible reps looks just like the representation mod variety mod conjugation. So I'll probably say character or representation and, mean basically the same thing. Okay, so for each irreducible component of the upper triangular on the meridian longitude representations, there are a few options. Under this map, here, this is a subset of C2. So maybe I get a curve, maybe I get a point, maybe I get all of C2. So I just want to take the components such that this is a curve. Okay, and then I'm going to look at the closure. Because like I said, there could be little, if you know any algebraic geometry, since this is an affine variety, I could end up with I'll end up with a Zariski dense subset of a nice algebraic set, but I might have some holes or something. Okay, so now I have a bunch of irreducible curves, and in a plane, or in the plane in C2, so these have to be cut out by a single equation. Okay, so fact. The set you get in, I should say, take the union of all these. Okay, and then what we get is almost uniquely determined by a single polynomial. And this polynomial is the A-polynomial. So let me first tell you what almost uniquely is. This polynomial is well defined up to multiplication by m and l. And the reason is, if you look over here, m and l are actually not allowed to be 0. Because I have to have an inverse. So the image is really in C star 2. And this defining polynomial is basically well defined up to scalar multiplication, right? So if I take the, so I guess I should say fact, you can choose an A such that the coefficients are in Z. Okay? Once you choose an A like this, then you can just take the content to be 1, meaning there's no prime dividing all of the coefficients, and you can make the leading term positive or something like that to make it absolutely well defined. So that's what almost uniquely means. I've taken it so the coefficients are integral, and I'll remark why you can do that in a second. And then I just remove any common denominators of this. I remove any factors of L and M. So the reason you can take it integral is because the defining equations for the representation variety are integers. And that it trickles down to here. Okay, so this is the A polynomial. And what time is it? I should say there are a few slightly different versions of the A polynomial, whether or not you account for multiplicity or not. So remember I said the first day that the difference between a variety and the ideal generating the variety, it's not an exact correspondence, one determines the other in both ways. And the difference is that if I give you, instead of this polynomial, if I squared it, the zero set is exactly the same. So in the character variety, the natural equations you get could be squares, and then the zero set's the same, or you could have two components of the character variety whose image is the same component in the A polynomial. So different people deal with the multiplicities differently. I'm going to ignore this issue entirely right now.
Once you choose these coefficients, what's the indeterminacy? You can't, because you mentioned this indeterminacy.
It's just once you choose it, it's just plus or minus 1. And then you could just take leading term to be 1 or something like that.
What happened to the indeterminacy?
So it's just basically an algebraic geometry fact. I have a curve cut out in C2. Then up to scalar multiplication, it's uniquely determined by a polynomial. And then the polynomial that cuts it out is, so I should say the curve is determined by a polynomial. And then that polynomial is well defined up to scalar multiplication. So the scalar multiplication, we're multiplying it in C. And if you know this is true, then you find a scalar multiple that gives you all integer coefficients, and then it's easy. Then you just remove any prime that divides all the integers until you can't do it anymore. And that has to be unique. Is it monic? Yeah, it is monic because there's a theorem that says there are ones in the corner of the Newton polygon. So the leading term would have to be a corner of the polygon. So you can choose it to be plus 1, and that'll uniquely specify. Okay, so just a few facts, and then I'm going to do my best to tell you about the AJ conjecture. So let's start with let's start just about a couple of facts about how the polynomial looks. You always get an L-1 factor. Some people's definition just removes this factor completely. So why do you get an L-1 factor? This is from the reducible reps. So if you're not complement, the reducible representations will all have to be identity on the longitude. And so your L and L inverse are going to be 1. It has a reciprocal quality. So after clearing denominators, AKLM equals AK 1 over L 1 over M. And the reason for that is I'm looking at upper triangular matrices, and my eigenvalue map, I took M and L. I'm going to have another, I could have taken M inverse and L inverse. That's a different choice, a coherent choice of eigenvalues. So my choice of the 1-1 entry is manifesting itself in terms of this symmetric property. So I'll show you the figure 8 example. So I'll tell you theoretically. So the character variety has several components usually. So writing like an algebraic geometer, That was the figure 8. So when I mapped it to the A polynomial, these two components each map to a component of the A polynomial. And in this case, they both become curves. So they're actually, realized in the A polynomial. And this one goes to the L equals 1 variety. So for every knot complement, the reducible component of the character variety, when it gets sent by the eigenvalue map, becomes the line L equals 1. And it's because for reducible representation, they're all characters of representations whose meridian corresponding to the abelianization. And the longitude dies in the abelianization, so it goes to the identity matrix. So the 1, 1 entry is 1. So you always see this. Yeah, so you can do a change of basis. That'll give you I don't want to think about it. Definitely a worst case birational transformation of your set for the A polynomial.
Polynomial is the same.
No, because the polynomial's in terms of your choice. Because I'm choosing L to be the eigenvalue of the longitude, my choice of longitude. If I choose a different homology generator that's longitude times meridian, then the new L will be like L times M.
So to get a not invariant, what do you say?
Well, you just take the standard framing of the knot, the blackboard. You take the standard longitude and meridian. A knot in S3.
Framed or something? Zero framed longitude? You have to pick something.
Yeah, I guess that people take the zero framed. Yeah. Well, I mean, there's like two canonical choices of longitude, essentially, right? So I guess.
You have to have some method of.
Yeah, I didn't think about that before, but I think you just choose that one. I think there's a preferred one that one takes. Yeah. But you can, if you know which meridian and longitude you've taken and you want to convert to another one, it's an easy change of variables. So another fact. Which I think in the interest of time I won't prove, but there's a cute little proof that it's actually a polynomial in L and M squared. Okay, so just to give you a sense of what it looks like, but the most important fact is a result of Dunfield for a knot complement in S3. If I look at the canonical component, then this is birational to its image in the A polynomial. Okay, so for the figure 8, if we just look at my little picture, the figure 8 had two components, canonical component, which consisted of the entire, I said it entirely backwards, right? All of the irreducible components, they're just one. This one has the discrete and faithful representation, and then there's the reducible representations for the figure 8. And then we take the eigenvalue map, and both of these stay curves under the eigenvalue map, and the reducibles go to L equals 1, and the irreducibles go to the rest of the A polynomial. And the theorem is that this map that sends the irreducibles to the A polynomial is a birational map. So if you're not an algebraic geometer, just think it's an isomorphism up to a finite number of points. Okay, so it's essentially an isomorphism. If you want to take projective closures, then they look the same. If you want to smooth and take projective closures, then they look exactly the same.
So this is for any just for
Oh, well, I said this, yeah, sorry, thank you. This doesn't make any sense otherwise. For me, all knots are the figure 8, so. Okay, so let me give you just a quick glimpse of the calculation for the figure 8. Okay. Yeah, exactly, therefore for all knots. Okay. Which I didn't put here. Okay. Okay, so with my presentation before, and I need to make sure I get the commutators right, so just excuse me for a second. I had W alpha equals beta W, W looking like that. Then we already knew that I could take rho of alpha. I'm just going to look at the irreducible representations, because we know the reducible ones are going to go to L equals 1. Okay, so I can take rho of alpha and rho of beta like this. And friendly fact, well, in this notation, both alpha and beta are meridians. So alpha is a standard meridian. And the longitude using this presentation is I didn't write it down. That's catastrophic. So I can tell you later, but sadly on my paper I just wrote L equals and I forgot to write it down. You can write the longitude as a friendly word in the alphas and betas. Let's call it Z. I can tell you later. Okay, so we know for rho to be a representation that equation that I wrote down before had to be satisfied. So r squared minus r times a squared plus a minus 2 plus 1 plus a squared plus a minus 2 plus 1 equals 0. Right? This is the star equation. All right, and so we also need rho of lambda to look like this. Which one do I have wrong? This one? This is it a plus? It might be slightly wrong, but that's what I have in my notes. Okay, so we need this. So what do? We write down what lambda is in terms of the alphas and the betas. We multiply those together, and we set the 1, 1 entry to L, if need be, the 2, 1 entry to 0, and that'll actually force the 2, 2 entry to be L inverse, but if we want to be safe, we have those three equations. Okay, so, yeah.
Lambda is equal to u to the power n
I know I don't want to compute these things. Mu to the n.
W star is W inverse.
And n equals 0 in this case, right?
But n is so that the exponent sum is 0.
Yeah, okay. So let's see. So this is mu. So W, so yeah, something like that. Oh, and I forgot an inverse there.
Then n is 0.
Thank you. Okay, there's a general formula for two bridge knots. I just can't remember these things when I'm standing at the board. So this is mu. So we compute, you take these, the 8 matrices for alpha and beta, multiply them together, and compare them with this. Okay, so we can compute it. We get, I'm just going to write down the 1, 1 entry. And I would recommend maybe not taking notes unless you hate yourself a little bit. I just want you to see kind of what you'd get into. And I'm trying to go fast, so I might not be faithfully representing all this. See, that was a little joke. Faithful representation. Nobody's laughing. It's very sad. Okay, so that's the 1, 1 entry. And then you get stuff over here, and stuff over here, and then stuff over here. Let's call this star star. How do you get the A polynomial? Well, first of all, I forgot to tell you, I told you the important fact, but I forgot to write it down. Since alpha equals mu, that means that A, the 1, 1 entry, is m. Okay, so we have our m's. I have my L, right? But I also have r's. Those are the 3 variables that are involved, right? So I need to get an equation from star, writing it in terms of m, and double star equals L, right? Because the 1, 1 entry is what tells you what L is. And so this is an equation in M, L, and R. So what do? Well, since it's just 2 equations, I could just take a resultant. You know, there are different algebraic ways that you can eliminate variables, but you can take a resultant. And you want to eliminate the variable r. Okay, that'll give you a polynomial in just the variables m and l. And so we get our A polynomial for L and M I don't want to forget my L minus 1 factor that was just from the reducibles. And this resultant it's not as bad as you think, but I do need a tiny bit more room. Looks like this. So not terrible. Hopefully I wrote that down right. Okay, so the one key thing is that the character variety in this case looks exactly like the A polynomial from an algebraic geometry point of view. So my character variety, it's just if you just focus on the canonical component for hyperbolic knots, then the character variety, think of it as this is a different way of looking at the representations. So in my character variety, I'm going to draw it this way. X naught, this point here, is given by chi, the chi-rho function, which is a function on, essentially on all of the elements of the fundamental group. In the A polynomial, I get they're birational, so they have to look kind of the same. The similar corresponding point here is given by the M and L eigenvalues. So what it's kind of saying is, well, and I guess I should also say that both of these correspond to a unique representation rho up to conjugation. Right? So for this representation, the character variety is just looking at all of the traces. And what this is looking at is instead of, well, you can think of it as traces of longitude and meridian. The eigenvalue is almost the same thing, but all I'm looking at are what the longitude and meridian do. And the one key reason that you can, in the proof that they're birational is that these characters on the torus subgroup, these functions aren't constant. They're changing as you move around the character variety. You can't get a canonical component where the longitude is always 2 or something like that. They're always changing. So that's a key fact in showing that essentially this is just the character variety parametrized by meridian and longitude. And Dunfield's theorem said that's all you need in order to know everything about the characters that deform in the sense of Abhijit to the complete hyperbolic structure. So all you need to know is the longitude and meridian. Okay, and now I'm going to potentially lie to you about the AJ conjecture. So tell me if I lie too much. If you have any questions about this, feel free to ask. If you have questions about the character variety, feel free to ask and I might be able to answer. If you have questions about the AJ conjecture, feel free to ask and I will almost certainly point to somebody else. So the AJ conjecture at the very basic level says that the A polynomial and the colored-Jones polynomial are intimately related. Okay, but the colored-Jones polynomial and the A polynomial are two very different beasts, right? I have a two-variable polynomial, and then I've got, this monster that lives in ZTT inverse. So I have to get from the monster, you can tell which side of the playing field I'm on, right? You have to get from the monster to the polynomial. He disagrees. He would go from the monster A polynomial, but that's okay. All right, so let's look at our colored-Jones polynomial. And I've never written these words on the board before in my life. Okay, so I have J, K of n. It feels weird. It really feels a little weird. And I'm going to let jk of minus n. I don't even remember if that's relevant, but just in case. Okay, and I'm going to define something that'll look totally tangential and will have nothing to do with the statement of the AJ conjecture. But when I'm done, I'm going to read you a paragraph from Stavros Garofalidis' paper where he tries to tell us why what seems to be a little insane, this insane procedure, might actually produce two things that look the same. Okay? So by way of motivating that, so it doesn't look like I've just randomly done crazy math on the board and said two things are equal, I'm going to define two operators. Okay, so shockingly, my operators are going to be called L and M. Okay, so how does L work? So I should say on functions f from z to c t plus or minus 1. So we should remember that this lives in a similar ring. Okay, so what does L do? L sends f of n to f of n plus 1. So that looks kind of longitudinal to me, right? I'm thinking in terms of the covering of the torus by the plane. The longitude moves it over. Okay, so does the meridian. I know, but you know. All right, what does M do? It just keeps f of n the same. Is it an n or a 2n? And it changes in a different way, in a different parameter. In the interest of time, you can prove this super easy. I verified last night that, okay, life isn't that good. It almost equals, and I need a t squared here. Okay, so you can actually easily do the computation, figure out what Lm of f of n looks like, figure out what ml of f of n looks like with composition. It comes out really easy. Okay, so this gives us the quantum torus. Also, the first time I've ever said quantum. T Okay, so I'm going to take C with t plus or minus 1, and I'm going to adjoin L plus or minus 1, M plus or minus 1. You can define inverse operators. Just for L, subtract 1, and for M, minus power. Okay, and so now I've got my, my ring here. I've got my L and my M, which I'm going to need. And I want to just mod out by my quantum torus identity. Oh, no, it just meant generated by. I'm just going to adjoin. I guess I just need this. Yeah. So I just mean we're going to make the ring where I throw in all my L's and M's and take the closure. That's probably the right notation. I have a problem with brackets. Angle, curvy. I tend to panic and forget which ones are the appropriate ones. Okay, so we're almost there. So if you don't like the operators, I just made this fun torus. You only need this part. Okay. So since the Jones polynomial lives in z t plus or minus 1, it naturally lives here, right? It doesn't have any m's in it, so you can think of it like an injective function from z t plus or minus 1 into t, right? So I'm just going to think of the Jones polynomial living inside of t. Okay, now my goal is to find a polynomial, right? I want to show that there's a relationship between the Jones polynomial and the A polynomial. So I need to get a polynomial out that has m's and l's in it. And the easiest way to extract a polynomial from a ring is to find a principal ideal. And then you can, principal ideals and nice enough rings, just like the A polynomial, have unique generators. And those are unique up to multiplication by a unit. That's why the A polynomial is defined by a unique polynomial, right? We started with the vanishing set. If you think of the ring theory side of the algebraic geometry, that's exactly why you know it's a polynomial. So you're looking at some ideal, the vanishing ideal inside of the coordinate ring, which is a nice enough ring. Okay, so what we want to do is do the same thing here. I have this quantum torus, which is a ring, and I want to extract an interesting polynomial as a generator of a relevant ideal. So we have two problems: what ideal to choose, and we need to make it principal, so I have a generator. Okay, the second part is not so bad. The first part, what is the relevant ideal? And it turns out the good ideal is called the recurrence ideal. Suggestively denoted AK, and it's just the left annihilator of the Jones polynomial. Okay, so it's the set of all P and T such that when you left multiply the Jones polynomial, I did something wrong. JK, oh yeah, N. That you get 0. Okay, JK, there. Oh, I'm good. That makes sense now. Okay, so this is the left annihilator, and I don't know how to spell annihilator. So in general, an annihilator ideal is one where when you multiply by it, makes something non-zero go 0. Okay, well, this is a left ideal, right? Because if you multiply it by something on the left, if P annihilated it, then multiplying by another thing is certainly going to be 0. Okay, so what we want to do, if life was good, this would be a principal ideal, and we would take its generator. But life is bad. So T is not a PID. Well, it's not a left PID. We have to be careful about commutativity. So we need to make T into a left PID. So we're going to add in the M's and T's. I had a nice way to say this in terms of fraction fields. Let me just see if I... Sorry. Here's a nicer way than I was going to say it. All right, so let's just so my notation doesn't get completely crazy, I just want to look at all of the parts of T except for L. Okay? So let F is terrible. H be all of the parts here. Okay? And essentially what I want to do, and I want to just think about it in the quantum torus. Okay, so the, mod out by the relation. And I just want to invert everything in H. Okay, so I'm sorry if I wrote something slightly wrong. So I just want the field of fractions of H. Okay, so I've inverted everything except for the variable L. Okay, so I can take denominators and everything else. All right, and I want to look at T twiddle, which is instead of this adjoin L plus or minus 1 in the quantum torus, I'm going to use H twiddle. So I apologize if my algebra is slightly not exact. What is it, LM? With with the rings, but I just want it to be clear that all I'm doing is inverting everything except for else. Okay, so now this is a left PID. And the key fact that makes this work is that the recurrence ideal is non-zero. And that's why it's called a recurrence ideal. This is because, and I think this is either Garofolitis or Garofolitis and Ley, the Jones polynomial satisfies, in normal person speak, a recurrence relation. Ooh, thank you. Okay, so if you have a recurrence relation, essentially if you can prove that the base case is non-zero, you can do an induction argument. Sorry, the base case ideal type thing is non-zero. You can do an inductive argument, and then you'll know that all of the things are non-zero. So I think that's why it's called the recurrence ideal. All right, so now I have a non-zero left ideal and a left PID. Now I can look for a generator. So we let alpha k be a generator for, well, let me write this. Okay, so AK is generated by some alpha k, and this is unique up to scalar multiplication, where here we have to be careful. This is in my field of fractions, right? Because that's what I made the scalars be. All right, so the question is, how do we write something? How do we write alpha? Well, let's just go back to basics. Alpha is the generator of an ideal that lives where? It lives in T tilde. Okay, so first pass, what does it look like? It looks like something here. So don't worry about this relation. We'll just consider it as a coset. All right, it looks like something written in terms of fractions of h times powers of L, right? So I can write it as a sum. Alpha k is the sum from, did I use I? J. J equals 0 to d of L to the j. Okay, I can multiply out powers of L to make them positive. And then this coefficient here, at first glance, is just written in H tilde. Okay, so my coefficient alpha kj is a function of t and m. And we know for sure that this is in H tilde. But what is H tilde? It's the field of fractions of H. So I can multiply out denominators, right? So, and it doesn't change the ideal I generate. That's the important thing. So instead of it being in H tilde, I can think of it in H. Okay, so it's in here, but I can clear denominators and take alpha kj to be in H, and then, we're just going to all have to believe Tang Lei, who I made sure I wasn't going to lie by looking at some of his papers, that then, because the Jones polynomial was defined over z, right? It's in zt plus or minus 1. It does live in here, but because it was originally defined over z, we can actually take them to be integral. Okay, so I can take it like that.
Clear fractions.
Oh, yeah.
There's a theorem, Petersen,
Yeah. Well, it cleared fractions. I can do that clearing fraction with reckless abandon because I'm just talking about generating the ideal, right? And those are units in the ideal. But there's definitely a theorem here. Okay, so now I have something that looks remarkably like a polynomial, right? And so now, I need to make sure that I don't have extra factors of, just like m to the 5 sticking out or something, right? Because the m's were part of this fraction field, I actually have no control over factors that don't have any L in it, right? So that'll come up in just a second. All right, so I have this thing, and just trust me that it's well defined. So what do? This is a function of t, L, and m. Evaluated at t equals -1. And the AJ conjecture is that alpha k and the AK are equal up to the powers, or up to polynomial factors in the variable m alone. Something like an m squared minus 1. And this is known for a bunch of classes of knots. I should say before that, if true, we know by Dunfield's result that the A polynomial can't be trivial for hyperbolic knots because it has a part that looks exactly like the irreducible representations. So that would tell us that this thing can't be 0. And the Jones polynomial couldn't be 0, right? So it would imply that the colored Jones isn't 0 for hyperbolic knots. Just to see how it might relate to things. And this is known for torus knots. And I'll just be a little vague. Infinite families, some infinite families of two-bridge and pretzel knots along with some various other examples of knots. But, this is pretty good evidence that worst case scenario is not so far off. All right, so I want to finish. Remember, the L and the M, I introduced them by these shift operators, right? So the L sent F to Fn plus 1, and the M sent F to T shift. So the way I presented it, I think it's not at all clear. You want to get a polynomial. So after you set up the quantum torus, you could see how this is how you might make a polynomial that is related to the A polynomial. But where did the quantum torus come in? And why is it intrinsically related to these? There's some big gaps in why you might think this is true. So let me just read the little explanation in Stavros's paper where he introduced the conjecture, and take from it what you will. So he says, it's not too surprising that the meridian variable m is identified with the multiplication map here.
This is foreshadowed by the Euler expansion of the colored Jones function in terms of powers of, I might say q, he says q instead of t. So in powers of t to the 2n and t minus 1. The physical meaning of this expansion is, according to Rosansky, a Feynman diagram expansion around a U1 connection in the knot complement with holonomy t to the 2n. Thus, it is not surprising that m is given by this. It's more surprising that the longitude variable corresponds to the shift operator L. This can be explained in the following way. According to Witten, the Jones polynomial of a knot is the average over an infinite dimensional space of connections of the trace of the holonomy around K, where the trace is computed in the n-dimensional representation of little SL2. To a leading term order, computing traces in the n-dimensional representation is equivalent to computing traces of an n-1,1 connected parallel of the knot in the two-dimensional representation. We saw that. Thus, increasing n by 1 corresponds to going once more around the knot. Since holonomy and longitude are synonymous notions, this explains in some relation, or in some sense, the definition of L. So, at least to Stavros, this makes total sense. Okay. All right, I'll stop there.
What information does the A-polynomial give about knots?
So because the canonical component is birational because the canonical component of the character variety maps birationally to the A-polynomial, then it basically gives all of the data that that part of the character variety gives. And lucky or unlucky for us, all of the other components, we don't understand what they do. So for, simpletons like me, it gives almost all the information because the information that could be lost is still a mystery. So some examples are that it tells you about surfaces that lie in your manifold, and it tells it in a very nice way. So I mentioned briefly that the character variety of the figure 8, it looks like this. It has two cusps itself that go off to infinity, and you can do an order of vanishing valuation here. Just look at functions, the zeros over poles, and there's a very extensive machinery that tells you that since both of these have this non-trivial valuation, that they both detect surfaces in the 3 manifold. And this is a highly non-canonical correspondence. But what is very nailed down is the exact, up to homotopy, the exact loops, the slope of the loops. Abhijit or someone talked about slopes on tori. So you know the slopes exactly. So what you know without thinking is that you either have the same slope repeated or you get 2 different slopes here. Well, the A-polynomial, for this, if you mapped out its Newton polygon, where you just put, so this is L and this is M, and this would be L and L squared and L cubed. And so I just take each monomial in my A-polynomial and I plot a point. Well, it looks like a diamond. And the slopes on the diamond, it's a symmetric diamond, I guess they all are exactly these boundary slopes that you would detect at infinity. So that's a huge thing that the A-polynomial does. And you can tell some other things, but I think this is what it's the most famous for. Thank you.